Hello, everybody. This is Mr. Comboy. In this video, I want to get into an ecological concept called biomagnification. So I'm going to start right in. Biomagnification has to do with certain toxins becoming more threatening to the organisms in the highest trophic levels than they threaten those in the lowest trophic levels. And I want to get right to it and talk about how humanity's been involved with this story. So, as you're probably aware, the greatest calamity of the 20th century and probably of the last few centuries was World War II. It had an incredible amount of suffering and death worldwide. Although for the United States, it was a gigantic victory that established a lot of wealth. And it was also a time to explore a lot of scientific breakthroughs and technologies that were used during the war to help win, but which after the war were kept as part of American culture and then part of culture of other nations that followed our lead. So during World War II, we had many soldiers who fighting in the tropics were very much threatened by lice and mosquitoes carrying terrible diseases. One such disease is malaria. You're probably aware that malaria still in the 21st century kills millions of people every year due to mosquitoes passing a parasite from organism to organism. So, trying to control soldier death by malaria was really important to holding out in our efforts against our enemies, especially in the tropics during World War II. So DDT was a toxin that was available to control mosquitoes by reducing their populations. And so it was used in a widespread way and was very helpful to the Allies. Now, once the war ended, the appeal of controlling mosquitoes so that life is more pleasant was a really strong appeal. We see a photo here in the bottom left of a couple boys who are playing around at a beach in New York in 1945. And they're running around really close to a truck that's spraying DDT. And we see that the drivers of the truck and the boys themselves don't look particularly concerned about the threats posed there. In fact, we see here a full page article in Time magazine, which was widely read in the 20th century in the United States. This advertisement, dated June 30th, 1947, is all about selling DDT and making people think about how it could benefit the food supplies that we use. So, if we can kill off bugs, then our apples will be nicer. We have a higher harvest. If we can keep cows and stuff free of insect and infections they cause, then our steaks could be of higher quality, and so on and so forth. And so the use of DDT became widespread really quickly. But in particular, its effect on malaria is what really caused cultures worldwide to use DDT. So malaria is a infection that's caused by a small one-celled organism, a eukaryote, actually, a protozoan, which infects mosquitoes of the tropics. And then those mosquitoes, as they bite humans, they let this protozoan go into the human blood. What we see here in this picture is protozoans that have invaded the red blood cells of a human and have caused those red blood cells to break open, creating the symptoms that come with malaria. And it became pretty clear that if we could kill these mosquitoes with DDT, that would help public health enormously. Now, the United States itself hasn't had a huge problem with malaria, partly because only a small fraction of it is in the tropics or subtropics. But if we think about our neighbor to the south, Mexico, where a much larger percentage of its country is in the subtropics or tropics, we can understand that malaria would be a large public health threat to them. So let's take a look at this graph. If we focus on the blue bars in the graph, those blue bars are related to the number of households in Mexico in the millions sprayed with DDT. And then on the y-axis on the left, the black line is telling us about the number of cases of malaria, and that's in the thousands. Well, we can see that in the late 1950s, when millions of households were being sprayed with DDT, at the same time, we see that malarial cases were relatively low. So later on, as we got into the middle 60s, early 1970s, we see that the number of homes being sprayed with DDT was less, and that resulted not that long after in a short term peak in the number of malarial cases. And so we see this cause and effect relationship between the use of DDT and holding malaria in check. And this is a really positive thing that saved a lot of people's lives. But it has caught up to us. And this is where we want to get into what biomagnification is. So, first of all, let's take a look at this graph. This graph is about what trophic level an organism is at. So, the first trophic level, of course, would be the first level from the bottom. Those are the producers, the things that do photosynthesis. And then the second level would be the primary consumers. Third level would be the secondary consumers, and so on and so forth. And so where you are in a trophic level depends on what your dietary habits are, right? I mean, if you're a vegetarian and you're eating only producers, then you're at this level. If you're somebody who's eating meat all the time, then you might be at the third or the fourth trophic level. But either way, what we want to start to get you to think about is that, according to this graph, what trophic level you're at has an impact on what concentration of toxins builds up in the mass of your body. So we can take a look at this unit of measurement. A nanogram is 1/1000th of a gram. So this is saying that if you eat at the fourth trophic level, then you may have accumulated as many as 100 nanograms of toxins in each gram of your own body's mass. But if you eat at a lower level, say here, then maybe you have about 1/100th as much. And so the idea is that as we go up the trophic levels from level 1 up to level 5, look at the fact that the amount of toxins in each gram of your own body mass is magnified or increased by a multiplication factor, right? From the second level to the third level, it looks like the increase is by a multiplication of 10 times as much. So, this is what biomagnification actually means. And we find that this trend applies across food webs and trophic pyramids worldwide. All right, so let's just break it down a little bit. This term biomagnification, we know that magnify means to make bigger. And we know that bio means life. So biomagnification of toxins basically means that we have an increase in toxicity of a living thing or of organisms in general as you move from one trophic level to the next in a food web. Now, what's really interesting is that it turns out that only one class of toxins will actually be involved in biomagnification, and that's the nonpolar ones. So we'll talk a little bit more about that in just a second. But so what that means is that if you're exposed to a polar toxin, that's not going to be as much of a problem as if you're exposed to a nonpolar toxin. And then how exposed you are to this problem, again, is depending on what trophic level you're situated at, which depends a little bit on your diet. So that's what answers this last question. Applying the definition, organisms at which level are most endangered by toxic levels? And the answer is that those at the higher trophic levels are most endangered. Okay, so want to take a little bit of time to talk about why it is that there's this distinction between polar and nonpolar molecules. Here are a couple toxins. We have ethanol, which cause lots of misery worldwide through drunkenness and all the effects that go with it. That's a toxin, but it's polar. It has that O on there. Remember, O is extremely electronegative, so we have this polar spot, which, remember, being polar means that it dissolves easily in water. We've discussed before how being polar is the same as being hydrophilic or water loving, meaning that it can dissolve well in water. Caffeine, this is another toxin as well. Not a big deal. It's extremely polar. It's polar there and at these nitrogen atoms. So this dissolves in water pretty easily as well. Nicotine is fairly polar due to those nitrogen atoms there. And so, if you have molecules that are toxic and are polar, they are actually a little bit less threatening because if they're polar, they dissolve in the water. And so, what they do is it goes to your kidneys and then to your urine, and then you pee them out of your body. Okay, so I mean, I'm not saying these things are harmless, but they don't accumulate in your body. But if we take a look at some of the other toxins here, such as DDT or chlordane, which is a common pesticide, hexachlorobenzene, these are all nonpolar. We notice that they don't really have any highly electronegative atoms, and then if they do, we see that they're symmetrically distributed so that the overall molecule is nonpolar even if it has polar bonds. So what happens to these nonpolar things? Well, we know that they're hydrophobic. They tend to stay away from water. So where do they go instead? They go toward other hydrophobic things such as lipids. So they go into lipids, which are really fats, in all of us. No matter how thin we are, we all have enough fat in our body to store up any of these non-polar molecules that we've been exposed to since the time we were born. So these non-polar toxins, they accumulate over our lifetime inside our fatty tissues. That's a big deal. So we can represent the consequences of this biomagnification in different ways. So I think a really simple one to think about is, let's look at this food web here in the bottom left, where we have some real small, simple organisms. Let's say they're producers. This is species A. So let's say these are producers and they do photosynthesis and they've been exposed to some toxins, and we see those toxins represented as red dots. Their predators, this copepod here, this is a primary consumer, it is holding on to just about every molecule of toxin, assuming that the toxin in question is nonpolar. So if we say that a red dot equals a nonpolar toxin, then this little copepod here, species B, that toxin is going to go into its lipids, its fats, and build up over its lifetime. And of course, that copepod is eating lots of individual algae cells over its lifetime. So if it holds on to most of that, then we have a lifetime supply built up in its tissues. And then that thing is eaten by this larval insect, which in turn is eaten by this fish. And this fish isn't going to live off of one of insect C, but hundreds or thousands of them. And so we see that the toxins are accumulating over time, becoming more and more concentrated in their tissues. And so now this larger predatory fish eating lots of individual Ds is getting more and more toxins. So if we think of this as the first trophic level, the second, the third, the fourth, and the fifth, hopefully this graph that we looked at here on this page makes a little bit more sense. Okay, we have similar representations of that for ecosystems involving mammals. So Not like you're thinking about eating polar bear or seal meat, but we do have some human cultures that do eat that, and they're at higher risk for exposure to toxins because of their habit of maybe eating some sort of higher predatory organism. If we think about species that are really famous and we care about, like beautiful birds of prey, like ospreys and eagles, we have the same trend. Now, this bottom picture is a little troublesome to think about, but it's worth considering, and that is that the baby isn't really at a higher trophic level than the mother all the time. I mean, they're the same species, right? And it's not as if the baby eats the mother, but consider that that baby early on is, of course, going to be nursing or eating, drinking the breast milk provided by the mother. And that milk is relatively fatty, and sadly, it does deliver some toxins to the baby. And, this is fairly inevitable, but it's a reminder that this matters to us as human beings. Now, for this slide, I would suggest that in just a moment you hit pause and you just read it over and really think about it. So do that on your own, and then when you're done, hit resume, and then we'll just talk about it together briefly. Go ahead, hit pause and think. Okay, so this is like really startling idea. We've spent a fair amount of our discussion of ecology talking about how trophic pyramids are shaped the way they are because the organisms at the top levels are going to get less of just about everything you could consider. They're going to get less energy, they're going to get less food, and so they support smaller populations and so on and so forth. Much of the food that they consume is, passes into their body, passes back out, since a lot of that food is polar, is broken down through cell respiration and other processes. But when we think about toxins, the fate is the opposite. And so these top trophic levels, they're getting less food and they support smaller populations with that smaller amount of food and smaller amount of energy. But they're getting more than their fair share of the toxins, which is kind of a double whammy that, you get little food to support your trophic level, but what food you get is more toxic. So that's kind of an irony that's important for you to think about. Now, this isn't just some theoretical idea, okay? We know through history the impact that biomagnification of lipid dissolving or fatty molecule, we know the impact that it has had on other species that are maybe a little bit more delicate or a little more sensitive than ours. So, a very famous story is that bald eagles nearly went extinct in the 1970s because as the prey that they consumed concentrated DDT in their own tissues, that DDT became very concentrated in the tissues of the bald eagle. And so when bald eagles lay their eggs, they tended to lay eggs that had thinner than normal shells. And so the process of sitting on the egg to warm it up actually would backfire, break the shells, and prevent the little eaglets. Eaglet is a term for baby eagle, prevent those baby eaglets from coming to maturity and thriving. And so there was a serious reproductive problem amongst bald eagles that almost caused them to go extinct. Until later on, some laws were passed that made DDT a lot harder to spray in the United States. And so bald eagles have made a gigantic comeback. They went from the verge of extinction to being fairly common. In fact, when I go sledding at Langham Park or go running along the Fox River Trail, I see bald eagles fairly regularly. And that's something that I couldn't see during my childhood, but enjoy seeing now due to dealing with this biomagnification by trying to outlaw some of these pesticides or at least limit their use. Now, in keeping with what I said before about getting milk from mothers, here we have an interesting photo of a orca or killer whale's calf nursing from its mother, reminding us that mammals fairly high up on the food web are particularly vulnerable to these same problems. But of course, as mammals ourselves, it is not something that we are sheltered from. So let's take a look at this graph. This graph is relating our per capita, which means per person meat consumption per day, to the incidence of colon cancer. This graph is about women specifically, according to this y-axis, but it applies, the same concept applies equally to men. So, what we're seeing is that the United States is amongst the most meat consuming of nations, and also simultaneously has one of the highest rates of colon cancer. Remember, the colon is the large intestine. So the idea is that if we're placing ourselves fairly high up on the trophic pyramid by eating a lot of meat, then we're exposing ourselves to a lot of hydrophobic toxins, fat dissolving toxins from other organisms. And then as those toxins move through our digestive system, they increase the likelihood of mutating some of those cells and leading to tumors. In particular, you may have heard about the danger of eating too many fish. I want to explain that just a little bit. So, mercury is a metal, it's an element that is naturally found as something found in coal. So, when we dig up coal, mercury is usually found commingled with that coal. And so, if the coal is burnt at a power plant in order to try to generate electricity, the smoke that comes out of the smokestacks is often laden with some mercury. So eventually, this mercury will fall back down to the surface and get into the water. So let's say that this yellow dot represents mercury that's gotten back into the water after it settled back to the surface from smoke. And it is going to dissolve inside the fatty tissues of organisms, and then it's going to biomagnify as we go up the food web. And so, if you've ever heard that it's important to have fish for the sake of, it's good nutrition and all that, but that you're not supposed to have fish too often, that's why. If you're in a place where wind blows mercury from somewhere else, then you want to limit the amount of fish that you're going to be consuming in order to avoid that toxin. I think this chart is really interesting and says quite a bit. So let's take a look at this row here. This is saying that the Environmental Protection Agency, the EPA, sets a standard for how concentrated mercury can be in fish for you to feel like you can safely eat it once in a while. But I want to point out to you that all the fish that have concentrations larger than that, most of them are predatory fish. And if we think about the marlin or the wild swordfish, these are really impressive predatory fish who also have very magnified levels of toxins in their biomass, in their biological matter. So in this video, I've tried to describe to you and show you some examples of this trend of biomagnification, which is basically saying that certain toxins that are nonpolar are kept in what fat we have and passed through the food web up to higher trophic levels, putting organisms near the top in most danger. So this is in contrast to a lot of other ecological trends. So it's important for you to notice. And we've already talked about how this has hurt some species, such as bald eagles and others, and poses a threat to cancer and other issues amongst our own species. But I want to end with an optimistic note and give a shout out to a really important hero in the history of science, and that is Rachel Carson, who wrote a really famous book called Silent Spring. She wrote it in 1962. It is not a very difficult read, so I highly recommend that if you're ever given a choice for an English class about something that you could read and report on, that Silent Spring is a great one. Silent Spring was one of the first books that really drew attention to biomagnification. And she wrote about it in a way that was really friendly to readers who maybe weren't scientists. It's a simple read, but very compelling, very persuasive, lots of examples, and that's where a lot of this lesson draws upon her writing. Many people credit Rachel Carson with having caused the public to become more aware of these issues and to put pressure on the government. And the government in the late 60s and early 1970s really did a lot of work establishing the Environmental Protection Agency, passing the Clean Air and the Clean Water Acts, which have provided some protection from toxins in general, including hydrophobic toxins. And it has really helped to reverse the decline of several species, and in some ways has made certain toxins become less of a problem for humanity than it has been. So, as long as we continue to follow the lead of these great writers and of scientists, and as long as we contribute to the expansion of science, we can hope for more optimistic gains. So, hope this makes sense. Excited to hear about your questions. Take care now.